So in this problem right here, what we're going to do is we're going to work our way through a thermochemistry problem involving an ideal gas, where what we're going to try and do is calculate the work, the heat, the change in internal energy, right, delta E, and then the entropy values, right, the delta S of the system, the delta S of the surroundings, and also delta S of the universe in this case right here. And so this is a problem specifically related to an isothermal but irreversible expansion. And so if we look through and read the whole problem, right, a cylinder with an initial volume of 10 liters and has 1 mole of an ideal gas at 25 degrees Celsius, the cylinder is fitted with a frictionless piston and the gas expands to a volume of 20 liters as the external pressure rapidly changes from 2.46 atmospheres to 1.23 atmospheres. Assume that the surroundings are large enough so that if heat is withdrawn from or added to it, the temperature does not change, right? So the two big things really to identify, right, is that this is a problem where it's going to be an isothermal problem, because the temperature of the system isn't going to change, right? It's going to stay at constant temperature. The thing that we can identify in terms of the irreversibility, right, is if there's a rapid change. Anytime you're going to have a rapid change in pressure and volume, right, those are going to be irreversible processes, right? And so that's going to change how you approach the problem, because instead of it being, essentially an infinitesimally small change in volume and pressure over time, at a constant temperature, it's going to be a rapid adjustment. And so that's going to directly alter how much work is done, how much heat is either released or put into the system, right? And that's also going to change the entropy of the system and the surroundings as well. So first things first, right? Let's write out all of the different components that we know that we have. So we have an initial volume of 10 liters, right? So that's 10.0 liters. We have an a final volume of 20.0 liters. We have an initial pressure of 2.46 atmospheres. And then we have a final pressure of 1.23 atmospheres. The number of moles is 1.00 moles. And then the temperature that we're at is 25 degrees Celsius, which if we convert into Kelvin is 298 Kelvin in this case right here. So now, right, because what we're doing is we're doing an irreversible expansion, right, that's happening rapidly, and we're changing the volume, but we're also changing the pressure, right? The thing to think about, right, is that because there's a change in volume, there's going to be work that's done, right? So work is going to be equal to negative P delta V in this case right here. Now, the pressure that you use is the final pressure that you're at. Right, so the way that you consider this to happen is that essentially the pressure drops very rapidly. It goes from 2.46 down to 1.23 atmospheres, and then, right, the change in volume happens. And so that's a very important thing to do, right? So if you calculate it at 2.46 atmospheres, you're going to get a very different answer for work in comparison. So, but because the what we're looking at here is going to be the final pressure, right? That's the value we're going to plug into this case right here. So we have negative P delta V. So if we just plug in all the different values that we have, the final pressure is 1.23 atmospheres, right? And then multiply that by the change in volume. And so the change in volume, right, we can just simply calculate. So change in volume is VF minus VI. So that's 20.0 liters minus 10.0 liters, which gives us 10.0 liters, right? So we just plug that in right here. So 10.0 liters, you get that. And so then what you get as your work is going to be negative 12.3 liter atmospheres. Now, liter atmospheres is a completely worthless energy unit, in my opinion. And so what we want to do is we want to be able to convert that into joules. And so the conversion factor for that is going to be multiplying our liters atmospheres by 101.3 joules per liter atmospheres, right? So if we take our work and we just simply take the negative 12.3 liter atmospheres and we multiply it now by 101.3 joules per liter atmosphere, what we get is negative 1246 joules in this case. Now, an important thing to point out is that because this is happening isothermally, that means that there isn't going to be a change in internal temperature, right? So we already know off the bat now, right, that delta E is going to be equal to 0. We also know, right, that delta E is equal to Q plus W, right, the heat plus the work. And so if we take that and we rearrange it, right, what we get is that negative work is equal to Q, right? And so we just calculated work, and so all we have to do is just plug that into here. So what we get is negative times negative 1246 joules. And so what the heat is going to be is 1246 joules, right? 1,246 joules, right? You can kind of shorten that down if you wanted to, right, to 1.25 kilojoules or so, right? But I'm just going to keep it like this for right now. Right, so we got that first half done. Now the entropy, right? So what we'll do is we'll calculate the delta S of the system, and we'll calculate the delta S of the surroundings, and then the delta S of the universe will just be the two of those added up, right? So in this case right here, the delta S of the system is going to be equal to n r natural log of V2 over V1 in this case, right? So we're only worried about the change in volume. We're not worried about anything related to the pressure, the temperatures in this case. So what we have to do is just simply take those, and so that'll plug and chug 1.00 moles times 8.314 joules per Kelvin per mole times the natural log of 20.0 liters over 10.0 liters. And so what we get is that the delta S of the system now is going to be equal to 5.76 joules per Kelvin, right? Because the moles cancel out right here. So that's the delta S of the system. All right, and so then for the delta S surroundings now, right, the equation that we're going to be using in this case, oh, almost messed that up, delta S surroundings, is going to be equal to negative Q over T, right? And so we have that right there, right? So we already calculated Q earlier, right? So that's 1,246 joules. So negative 1,246 joules in this case, right? Divide that by the temperature, which is 298 Kelvin. And so what we get is negative 4.18 joules per Kelvin in this case right here, right? So that's the delta S of the surroundings. So now delta S of the universe is equal to delta S of the system plus delta S of the surroundings. So if we plug in the values that we calculated, 5.76 joules per Kelvin plus negative 4.18 joules per Kelvin, what we get is that the delta S of the universe is 1.58 joules per Kelvin, right? And so that's still a spontaneous process in this case right here, right? Because delta S of the universe is increasing, right? It's greater than 0 in this case, right? And so that's how you calculate those three different components for this problem right here.